But now we have basically a quick introductory tutorial to Julia and JuMP, so you can kind of know a little bit about what's going on. So I guess we were a little bit late on tweeting the. I actually lost it. Oh, yeah. So we're a little bit late on tweeting the instructions. So if you actually want to follow the tutorial online, there's instructions here in this GitHub page. And basically, the only thing you need to install is you need to install Julia, and there's instructions exactly how to install Jupyter notebooks, and and basically all the packages you'll need will be installed automatically on the when we actually run the notebooks. And so if you're having any trouble installing anything, did Miles disappear? Oh, there's Miles over there. Bug Miles. I guess you can, and then you can bug in English and or Spanish. So, and I know it says like even Chilean. He's like, so I'm thinking like actually when was the time we gave the tutorial, the first JuMP tutorial in Adolfo Ibanez? Was it? But what year was it? It was 2015. It was like 4 years ago. There was a tutorial, and it was not just in Spanish. It was in Chilean. So the diet problem had Chilean sandwiches. I think chacarero. So feel free to ask him if you want to install it. And again, the webpage will be there, and all the packages will be there in case you actually want to run over them after the tutorial. And there's a ton of different things to cover on Julia and JuMP. So if you have any questions, just stop me, and I'll let you know if you have any detailed questions or any general questions about how Julia and JuMP work. So let me see that. Can everybody see the screen in that size, or should I make it bigger? Good enough? Okay. So basically, let me start first with talking a little bit about Julia. So Julia is the underlying programming language on which JuMP is built in. And the syntax is very similar to somewhat between a mix between Python and MATLAB. So, for instance, like if I want to, and I'm actually showing you now Jupyter notebooks. So you could also go and open the repo. So the repo, and you'll see in the instructions, is the place where you can install the basic packages. So it's just a command line interface where you can actually write down and write Julia code. So that's sort of like a terminal-like. But if you looked at the instructions, you can install Jupyter notebooks. So if you're not familiar with Jupyter notebooks, it's a notebook that looks like something like a Mathematica notebook. But Jupyter means Julia, Python, and R. So instead of having on the back end, you can have either one of the three languages. And that's a nicer way of sort of doing demos or actually running prototype code, because you can run them on notebooks. And basically, each notebook will have some cells and where you can write down the Julia command. And if you hit Shift and Enter, it just executes the command and will give you the output. And if you see that star, that's processing time. So hopefully, of course, demonstrations always fail. So I'm expecting everything to crash pretty quickly. So just to get started, one of the important things that Julia has is that it is a type system. So data types are important and make a big difference, and it's part of the performance. You'll actually, one of the plenaries in the afternoon, the first plenary, will tell you a lot about how is it that types make Julia fast, or even much faster than Python or MATLAB, and sometimes even faster than C or C++. So I'll tell you a little bit. So basically, the simplest types would be integers. And the interesting thing is, like here, I didn't really declare the type, so you don't need to explicitly declare anything, but there is an underlying type, and you can actually write type off to actually get to know what the type it is. And in this case, it's a very specific type. It's saying it's an integer written in 64 bits, and it's sort of like the most low-level type. You can also type with write down with floating point numbers, and we can see that the type of 1.1 is a float 64. And this is something that Julia will do. You wrote -1.1 and then immediately realized that, oh, you want to actually write a float. So I'm going to declare now this object will be float 64. And basically, a lot of it will be Julia will infer and figure out what type you meant. And sometimes it will guess exactly what you meant. Sometimes you'll actually have to explicitly write things. So for instance, if you really wanted to work with integers, if I would write down there type of 1 instead of I write 1.1.0, it will now be a float 64. So if I did that, now all the computations are going to be a little bit more expensive than they would have been otherwise. So you want to keep track that you're not getting types that are more complicated than you wanted to. Types can also be specialized. So for instance, like one of the nice things is that if I write pi is a constant that's defined to be pi. And if I look at the type of pi, it's telling me actually it's an irrational number. It's a little bit more specified than a floating point number. Now, I guess I should tell you how to write pi. So the other great thing about Julia is that all the characters could be general Unicode. So if I were writing pi in some other language, I would actually have to write down pi, and that's maybe not as aesthetically pleasing. You can actually get pi by just typing, and I can figure out how to type backslash. Oh, there we go, backslash pi, and I do tab. It will actually go and replace it by its Unicode, the Unicode character. And a lot of the other like basic characters will also show up with similar slash commands. Julia also has native support for complex numbers, and I can write it down by just saying like the real and the imaginary part. And if I ask what the type of is, it's going to be a complex number. And that complex number basically has inside its real and its imaginary part. And in this particular case, both the real and the imaginary parts were integer. If I would actually go and type the make one of them a float, then it says like, well, this has real and imaginary parts that are also real. So it's a combination of, you can have real complex or integer complex numbers. Strings are always useful. So strings you can declare by just using the double quotes. And there's a type that actually is strings that defines them that way and has different properties. And again, if you want to write down Unicode strings, you can. It's built in, completely built into the system. So if you want to label things with emojis, you can actually label things with emojis. If you can write variables to be emojis, you can. And it's actually kind of fun thing to do for classes or presentations. Another important type of is symbols. So if you write down colon my ID, this is not a string, it's a symbol. And for instance, variable names will be symbols. And one of the nice things about Julia is it can read its own code and modify its own code. That's one of the things that makes JuMP fast and easy to use. And the type for these things is a symbol. And that's special, it's not just a string, it's treated in a more special way. I'd say most important when you're looking at more advanced Julia things that we're not gonna cover, but it's something good to know. So again, for math, it's extremely easy. You can multiply complex numbers. Everything works out okay. One thing to be careful with is, I think I once said something like floating points are the tool of the devil. You should be very careful with floating points. So for instance, if you actually ask that they're equal, these two are not exactly equal just because of numerical errors. And in fact, you can check that the difference between numerical errors is like a very, very, very tiny float. But equal means that they're exactly equal as floating points. It means they're equal at whatever type they are. And in this case, these two are floating points, are not going to be equal. So the great thing is that Julia gives us a built-in approx comparison that now says that, yes, these two things are equal up to the numerical precision of the type. So that's another thing that's useful. And again, it'll be up to the numerical precision of the type. I could have a type, a float of higher precision that actually would be easy. They might be equal in given precision and none of the other one. And in fact, you can actually pick, there's a way of actually picking the precision you want to compare. So whatever is the epsilon that you want to use to compare two numbers, you can also define it and use it. But in this case, it's just the precision of the floating point. And again, that also causes trouble when you actually have floating point numbers that are nearly equal. Sometimes things go weird, and that's what basically the usual warning is be very careful with floating points. I really like this example. Is like floating points are not even associative. You added this number is 1 plus 1 to the minus 16 minus 1 to the minus 16. They both should be 1, but if I write it first with parentheses on the first part and then add this, that's different than doing this before this. So be very, very careful with floating points. And again, that's something that is like easy to see. Julia kind of exposes nicely, but it's something that has to do with floating points, nothing to do with Julia. This will happen everywhere. And if you're written code in C, this is like the worst bug to try to find out when you're never compare floating points with equality. Another great thing about Julia is like some of the stuff is very similar to MATLAB. So if you're using Python, Python is great for a lot of computing purposes. But if you try to do linear algebra in Python, then you need to install NumPy or SciPy, and things start becoming really annoying. Julia has built-in linear algebra. So in particular, I can write down vectors. So I can write down vectors like that. That's the notation. And a vector will basically be an array. And in this case, it knows that it's an array of integers, 5 and 6. So that's what's showing up here. And it's an array that has one dimension. It's a one-dimensional array. That's what a vector is. I could also write down two-dimensional vectors to write down a matrix. And you can write down as high-dimensional arrays as you want. If you want to work with tensors or higher-order tensors, you can as well. Now, with these matrices, I can do linear algebra. So if I really want to solve the system AX equal to B, I can use the usual MATLAB-like notation of dividing by B, and I will get basically the solution to the linear system. And again, I can see that, well, basically, if I plug in that solution that I got over here, it's exactly satisfies the linear system. You should be careful about multiplying the working with dimensions. So if you get the dimensions wrong, you'll get an error that says I cannot really multiply these two. And I believe that if I did a transpose, that will work okay. So interesting enough, I guess here I multiplied B transpose. So it was the Kronecker product. If I did it the other way around, it should have given me the inner product, and that was exactly what I got. So be careful about sort of like row, column, or column vectors. You need to make sure to get them right, the dimensions, and basically you can use the transpose to make things work. Oh, I guess this is exactly what I just wrote up there. Another useful construct is tuples, which are sort of some kind of static version of an array. So you can use them. It's very useful to pass in parameters from one place to another. And tuples will be also a type of container like an array, but it tells you this is a tuple that has a string, a float, and a symbol. And it's very, very statically defined. And you're not going to add anything extra to the tuple. You cannot extend it, and the types are fixed, and everything's sort of explicitly fixed to that particular case. You can access elements of the tuple the same way you would access elements of an array. You can sort of unpack them, so it's a useful notation. So you can pick that T that contains 3 elements and say, well, give me the 3 elements separate, and you can access one of them. And you could also name the tuples. So in this particular case, again, I have my string, my float, and my symbol, but I'm naming them. So now I can recover the string by saying t.work. So there's going to be multiple ways of accessing tuples in Julia. Another useful construct is dictionary. So basically, these are going to be general arrays that are indexed not by numbers, and that can access basically in this particular case they're accessed by 1, 2, and 4. So I can get element associated to 2. And in this particular case, it's telling me it's a dictionary whose indices are integer and its elements are strings. But I can have a more complicated dictionary whose indices are any. So any will be the type of, could be whatever, and that gives me back also anything. Could be float strings that I won't know, and could be as general as I actually want it to be. I guess one thing that I should mention they start from 0, you're wrong, but it should never start from 0. Although I have to say that I had no idea that Alan Ellman had a Twitter account. He has never tweeted. I think now he has 2 followers. One of his PhD students and me, because they found him. And by the discussion of 0 index or 1 index, we managed, I think his account's been like 2013. So for a while, and then suddenly we were tweeting and fighting about like a 0 index versus 1 index, and his tweet was like, oh, I actually have a solution. Somebody at MIT Math once told me that the way to fix it is just do 1/2 indexing. So you could actually use dictionaries to do a 1/2 indexing as if you actually wanted to, in case of, but just, but in Julia, the default arrays start from 1, which is the right thing to do. Again, I guess so here's an example of a little bit more general dictionary that, again, its indexes are strings and its elements are something weird because they have an integer, a float, and a complex number. But the interesting thing is that Julia recognizes those types as numbers. So it's explicitly telling me that these elements are numbers, and I'm only going to see numbers on this dictionary. And numbers can be treated nicer. So for instance, I know that I can add numbers. I can multiply numbers, and there's going to be functions that are going to work with numbers in a generic way that doesn't overfit to integers, floats, or complex numbers. We want the code to kind of specialize. So Julia's going to be compiled. I'm going to give you some examples a little bit further down the notebook. Julia will compile the code that you're running just before it runs, and it will compile it to the most specialized type that it can. So if it was integers, it could do maybe operations much faster than it was floats. If it was like or complex numbers. In this case, it will have to compile the code that only uses numbers that may be a little bit less specialized, but it will work. And this is something that is transparent, so you don't have to really worry about it. But it could be a source for lack of performance because you didn't have as specialized code or specialized types as you actually wanted to. You can, again, like, I guess here's a little bit more general one where you can actually nest, and you can see that now this is a dictionary that still the indices are strings, but the elements that I'm getting are any because they have a number, an integer, and another dictionary. So I can also nest it. And again, in this case, it cannot specialize more. There's no type that contains dictionaries and integers. So it cannot specialize. The most general one is anything. And again, if I want to access the nested structure, I can just access it by doing the double brackets. For loops, I guess useful construction are very natural notation. Just like I want to do a for loop from I from 1 to 5. This is the basic notation, very similar to Python and other codes. I can also I can iterate over almost anything that I can iterate. There's a construction for things that are iterable. So this is an iterator goes from 1 to 5 in integer increments. But I could also iterate over an array that has floating point numbers. And there's many more complicated things that I can iterate over. In particular, for instance, I can loop over the dictionaries. And in this case, I want to recover the key and the value. And I can write down the code that will make me loop on that. And if you have any, you could define your own new data structures or as complicated as you want, as long as you define some basic functionality, you'll be able to iterate over those as well. Control flow also, I guess, would have like if, then, else. The traditional ones, we have logical operations. So I guess this one's like an easy example of there's a for loop, and it'll basically show you how to do the control flow. It's basically nothing dissimilar to most standard languages. Another thing that actually is useful in Python and other languages are list comprehensions. If you really want to construct an array, list comprehensions are an easy way to actually do that. So imagine that it's like I'm writing down the for loop that's constructing this array, but instead of having to build a for loop, I just kind of embed it inside the actual array. And you can again also do it for multiple dimensions to build more complicated arrays. See what we're doing on time. You can also add conditional statements into arrays, and this is actually going to be something useful that we're going to see later in JuMP. This kind of notation for constructing arrays will also be the kind of notation that we'll have when we're building a constraint or set of variables. We're going to be able to use this exact same notation in JuMP. So for instance, if I really want to write down to filter all the even numbers, I can just like write down that condition, and it will only generate the elements that satisfy that condition. And basically same construction, I can also do it to write down dictionaries. I guess the next thing we want to do is like defining functions. So functions are defined just by writing down function, the name of the function. In this case, there's no parameters. So there's sort of a simple function. If I want to give it some parameters, I can just write them down like that. I can't type the parameter. I could say that this is only for strings. So let me give you an example. So if I do this, I'm going to actually be able to print any of the, let me see if I have an example later on. Nope. I can write down that function that will take anything and try to print it. So as long as whatever that type was can be printed, it'll be okay. So I can call it with a string, with a float, or with a symbol. I could have actually done another version of this. And now I cannot find the underscore here. And I can type it to be integer of type integer 64. If I now call that function, it will throw an error saying like, well, you're calling it with a string, but I only define it for an integer. So what I could alternatively do is define, so this function will now has only one method that's defined for integer 64. I can actually go and say, define another one for strings. And now I could do something like, now I cannot find the quotations. And now, let me actually add the space there so it's not ugly. Then I actually have a method that will be different that will behave differently for strings and for integers. Okay. And again, what I did over here is I didn't care what the type was. So then somebody defined print line for strings, for integers, for floats, and for everything, and it does something to actually print it. And we didn't have to worry about it. A lot of the functions will have multiple methods that will behave differently for different types, but I usually don't have to worry about it on at least the first run. So I could have just done this, or if I really have a reason to think that I want to actually write down different methods for different types, I can actually do that. And this will, I'll comment in a couple more cells, and like this is a potential source for a lack of performance in Julia when you actually do complicated things and are not really paying too much attention. You also can actually have values that are named. So that's sometimes useful in case you have a lot of parameters and you don't really want to remember the order of the parameters. You can actually name the parameters that the function is getting. You can also have a default value for the parameter, and you also can actually add optional parameters. So in this case, y has a default value of 2. So if I call the function just with 4, it will assume that y is 2, unless it explicitly redefine and tell you, no, I want it for a different y. So that's another useful construction for adding default values. I guess I've been telling you along the way about types. So for instance, again, Julia will infer what types it is that you're using. So in this particular case, I have an array that's only integers, and it's going to go and define it as integers so that it could potentially call, you might actually go and say, I'm going to do something on a vector, and maybe you have a function that works much better with integer vectors. You can actually, Julia will be able to recognize and call the most specialized function to actually do that. But if you had mixed floats and integers, it will actually have to give you the highest level that it can contain, which would be float, and now it might not be able to call the most specialized function that it could use. It will still work, but again, it might not be as fast as it is. So if you know that you can do faster things with your types, you want to make sure that you're keeping track of that. I don't know exactly what I want to say with immutable objects. I guess the main thing is basically if you're passing around arrays, you can actually change the content of the arrays inside a function. If you're passing around integers, you cannot change the integer. So there's types that are passed that cannot be changed when you pass to a function, types that can be changed, and there's a handy way of actually checking if they're mutable or not, which is with the command is mutable. But in general, I would say it's fairly natural. I don't know, is there any immutable, anyone that's not, I guess it's like it's a little bit of a chicken and egg, because I was going to say that it's rare to not realize what it is that actually is mutable and immutable, but then maybe it's because I'm also used to it. But I cannot really think about anything that is like not completely obvious.
What about complex?
Complex numbers would be, the complex numbers should be immutable.
Sorry.
Oh, what did I do? Oh, I moved to JuMP. Now.
Y 2.
Worse is like I had a student visiting from Skoltech and he had a Russian keyboard. That was actually right. So it is immutable as we expected.
Big integers.
Big integers. Big int would be mutable. They should be immutable. Aren't they? Yeah. How do I write the? Can I actually type a type here? Interesting. Oh, no, wait a second. No, because that's a type.
Work like the parentheses after the beginning.
You mean?
I mean, one.
Oh, like this. There we go. Okay, good.
Okay.
They're not in. So
The API is immutable, but they have to be garbage collected because they call C library that needs the clicks free memory, so they have to be immutable, which is annoying, but just pretend that they're immutable.
Good. Hence the is immutable functions. So you're gonna find
You
out.
won't be able to use a dictionary without beginning, right?
No, you could use a dictionary. You could have a dictionary with big ints, yes.
But if it's immutable, I mean, will that be a problem? If the key is immutable.
Oh, if the key is a big int.
Yeah. That will work.
So there is this thing called discourse where you can definitely complain. Like, and if you go and see the it's fun to see the threads on how things were decided. And I think it's like I still keep seeing new things on discussions on. What was the one that I was looking at? I was like, the issues with curl. Some issues with curl that recently were showing up. So. Okay. I guess that's the other one. Another way of actually defining a function is by the simple notation and just like defining the function equal to something without having to explicitly declare function. Now, if you see here, it's a function that actually has any parameters. It doesn't have different methods. But if I call it with an integer, this will actually, Julia will pick the function and compile it. And it will compile it by realizing that, oh, you're being called with an integer. So Julia will compile the specialized function for integers. And like an easy way to actually see what's going on is that you can type this macro, which is, like, I haven't talked too much about macros, so it says code warn type that will actually tell you what version of add you're actually running here. And you're running the version for int64. If I do it for floats, it'll be compiling the version for float64. So it doesn't really need to know what the number was, but it needs to know that you're calling it for floats, and it will compile that version that will be specialized for floats. And that could be a huge performance hit depending on what you're actually running. And Julia's very clever at figuring out what are the types, and you call a lot of functions one after the other and do a lot of different things. In general, Julia is very good at figuring out that you actually got what are the types that should happen. If you call this function with an integer, you're going to get back an integer. Let's say if you're adding two integers, you get an integer. If you add two floats, you get a float. But you might actually write complex code that actually doesn't do that and might be called an integer. But let's say if the integer is 1, you get an integer. But if the integer is greater than 1, you get a float. If you write code that does that, then suddenly Julia cannot predict what your types are going to be, and it cannot really optimize to the as well as it could. So that's and I would say generally you'll see these if you write down this macro in your function, you'll see some red things that say, you know what, at this stage, I don't know what this type is. It could be any, or it could be a multiple things, and you'll see that it cannot specialize as much as it could. So there is a whole section in the Julia manual on performance. So I would say like if your Julia code is not running way faster than Python or MATLAB and close to C speed, and your code is complex, there's a chance that you ended up in some pitfalls that were definitely non-obvious, and most of them are described there on the performance tips. Finally, there's like there's a package system that used to be annoying, and now it's really good. It's fast and has some like nice features that we're actually going to use in for the JuMP tutorial. To get the packages, some packages are built in, some packages you need to add. To load them, you can load them with using or import. And in particular, if I want to generate random numbers, it's a package that's in the system, but it's not loaded by default. So by just saying using random, you'll be able to load the random numbers. For instance, for JuMP, we're actually going to use, for JuMP, you'll need to use the package JuMP. You also need to add them. So in particular, so random is a package that's built in. JuMP is not a package that's built in. So you need to add it. So you can add it by loading the package manager and adding JuMP. There's also an interactive way of adding packages that you can actually see a nice description in this video that you'll get with the with this closed square bracket. There's actually an even nicer feature on the latest package manager that allows you to sort of save the state of your package system that you have right now with the exact versions that you want to use, save them to a file, and then you can get somebody to import them so they load it automatically. And that's exactly what we're actually going to use. So this set of commands that were in the install instructions, when you download the files for the tutorial, it'll go and install all the versions that we know will work for the tutorial, so you don't even have to worry about it. You could have installed it manually too, but it's really good for quick tutorials or for classes where you want to make sure that if I want to know about what the class operator does, I just question mark plus, and it will tell me that's what plus does with some examples and some details about what's going on. I guess I already showed you that method error that above when I actually defined this function that only was defined for strings, for integers when I called with a string. That's a usual error that you'll get when you're calling a function, let's say for complex numbers. The ceiling function is not defined for complex numbers, so this is one of the errors that you get. And errors are getting, they're still sometimes a little bit obscure, but now I'd say that they're getting much better on describing what's going on. But sometimes you'll see there's a lot of extra information that might not be obvious the first time you use it. But basically here it's telling you, I don't know how to do it for complex numbers. The closest thing I can actually use are these definitions that I have. So sometimes it's a matter of like, oh, actually, I typed it to something that was not what I meant, and I really could have used one of these. Or in this case, no, there really is no easy way or natural way of defining ceiling for complex numbers. Okay, any questions on Julia? In general, okay, so let me switch to the, so I guess we have half an hour for switching to the JuMP tutorial. So I guess I usually start this demo. I usually start by asking the question of passing along. So I usually start this question with like, how many people needed visas to come into the country? And I think it's harsh. I think it's like interesting enough. It was like one person, although technically I think technically it's 2, because Chris is Australian, so Australians do technically need visas, but you get it when you're coming into the country. You don't really get it. You don't really get it beforehand. So I guess 2 people needed visas to come into the country.
It was 3, but the third one.
Oh yeah, actually technically there were 3 because actually they couldn't.
I think the stream stopped.
Oh, I stopped the streaming.
Let's say yes, you did it. I don't know.
You stopped the stream.
I don't know what happened. Test stream. There we go.
Julie is also very good at recursion. So. When did it stop? Just now, or has it been stopped all the time?
An hour ago, no, 2 minutes ago.
Okay, so I guess moral of the story, we should monitor.
Just share it, the screen sharing.
We'll figure. I guess. Like, now we need to. We'll beta test it. This was the beta test to make sure that we can stream the important talks. This like nobody cares about missing this. Okay. Anyway, where was like so? My question was like this started at some point about visas, and the question was like, what's the minimum number of passports you need to be able to go to every single country in the world without a visa, any type of visa, either entry or not. So maybe I'll ask the question like, how many passports do you think you need to be able to go to every single country in the world? Any guesses? 10? Okay, who says more than 10?
22.
22? Cheating. Who says more than 22? Okay, I'll show you and it'll be pretty evident why. So I'm basically, I actually was discussing this and I found a page that actually has this passport index, which is it's like a really funny page because basically what they do is something like it's lawyers that work with high net worth individuals that want to be citizens of the world. So basically they tell you how to get the passport. And how to get the passport is non-trivial issue. Some of them are incompatible, but so to keep things easier, I'm gonna just say like, suppose you can get any kind of passport, like instantly. What's the fastest way? Forget about if you can or how long it takes. Just get them. So I'm gonna write down a mixed integer problem for this. So the first thing I did is to run this, I'll need a lot of packages. So I'll need basically JuMP, a MIP solver, and I also added a mathprog base. So we can actually import all the packages by running that command. And if I run it now, it's not gonna do too much. But when I run it at the beginning, it basically downloaded and installed all the packages that I actually had written on the manifest, so the packages that we needed. But if you already had JuMP and GLPK and mathprog base, math opt interface installed, you wouldn't have to do it. But this again is a useful feature when you don't want people to worry about installing packages. So the next thing I want to do is like, luckily this information was there's a GitHub page that actually had all the data on the passport, so I'm going to import them. Good, worked. I'm basically now loading the data, and I'm using the package delimited files that allows me to load CSVs easily. And basically, this is just a little bit of code to translate the information from the format that was on that GitHub page into format and information that can actually write an optimization problem. I'm going to run that. And so the optimization problem that I'm building to be able to ask that question is, I have variables that are passport indexed by the country, and I want to minimize the number of passports that I have, subject to I need to cover every destination in the world that I actually want to go, and I'm covering it if that particular passport allows me to go to that country without a visa. And that VF is basically the data that I loaded from the file. So this is the mathematical optimization problem, the way that I would write it in paper. And if we'll see that basically I can write down almost the exact same thing in JuMP. So what I need to do is I'm loading JuMP and GLPK, which is a MIP solver that I'm going to use to solve this problem. I first start declaring a model. So I say I'm declaring a model, which is defined in JuMP. I could also written to be more precise, JuMP.model. I'm telling it, please use GLPK as an optimizer. To define variables, I just say add variable for this model. The variables are called pass. They go from 1 to the length of countries. So if you remember that comprehension had 1 to 4, 1 to 5, I can use the same notation here and more complicated notations. I'm making the variables binary, which are these constraints over here. Then I need to add these constraints that I declare by the add constraint model. I can again use this part to declare using a comprehension notation to declare this for all destinations in the world. The sum, I can use basically the same notation as a for loop or a comprehension to say sum over everything that goes from 1 to the length of centers. And instead, if I had some data structure that had all the countries on the world, I could have done for I in whatever that data structure is, and it would have worked. It would iterate over that automatically. And then it's greater than or equal than 1. The objective, again, is minimizing the sum, and in this particular case, that pass is some container. So if I say sum without any details on what to sum, it will just sum all, no matter what the container is.
So VF is a matrix?
VF is that's a very good question. It should be a matrix.
What is VF?
So VF is the data that I loaded from the file.
What is VF?
Visa
Visa-free, yeah. Yes. And what is VF? Yeah, it's an array of integers.
You just printed out.
What's the best way of printing this? Yeah, so and basically what I did was like there was like some information here, like I think there is 1, 2, 3 visa on arrival or no visa or something like that, and I just transformed it to 1, you have a visa, you can go without a visa, and 0 otherwise. And finally, this command just says, well, optimize the problem. I can get subjective value, and I can get what I'm getting here is basically I'm getting the value and that I'm combining. I'm getting the value of these variables. I'm checking all the ones that are equal to 1, and then I'm actually writing down, instead of printing the number, I'm printing the name of the country. I guess you already can see it, but let me run it. I guess it's perfect good to show you that pre-compiling JuMP. So as I mentioned, Julia is compiled. So the package, you need to compile JuMP. It used to be that you had to compile every time you said using JuMP, it would compile something. Now because it's saying pre-compiling is that it's pre-compiling the package, so you can have a copy that's compiled and it's sort of like cache, and you won't have to compile it again next time you use it. But it can take a little bit of time. So, but think about this is when you're compiling your C code and running make. This is exactly what's happening. The thing is that it's happening kind of online, and that's why sometimes messes up demonstrations. I would blame the computer as being slow too.
Yes. Can you write that sum constraint with a matrix? Matrix with it?
And what do you mean?
You basically have a matrix type of vector.
Yes. It's you should be able to. So actually, let me try that while this thing is compiling. So I could just go and say, basically, VF times pass. Will that work? Should work. That is, like, it will recognize that the one that I meant one. Oh, yes. Let's see. Oh, yeah, it might be VS transpose. Okay, interesting. Yes, it was VF transposed. But the interesting thing, the matrix was square. So this would have been a very hard error to catch. You need one password. You only need Micronesia. Okay, now it actually, oh, this is a really fun warning. What is it? Huh, interesting. Is that new? We'll do an issue right now. But it's a warning. It's saying something about it's like you might have done something that was slow in JuMP.
It's like a full stack.
Oh, it's a little, okay. Because it's not really doing the linear algebra the best possible way?
Exactly.
Okay.
It's not special.
And was that because of the transpose?
Or the transpose multiplication, I'm not sure.
Ah, interesting. Oh, no, because it was a warning. Maybe it doesn't show it twice. Yeah. Huh? It is an issue, so okay, good. So another thing is like, if you find issues, you can go to GitHub and generate an issue. Just be warned, depending on the issue, you might get as like, oh, that's a great issue. Maybe you would like to generate a pull request and fix it yourself. The great thing is that you can actually fix a lot of things, even if you're not an expert in Julia. So you're using it and you're using it a lot, then that's usually enough to actually fix small things in the code, because most of the Julia code is written in Julia. So you can actually go and fix it without being an expert. So you're immediately invested on the code. So Oscar was wrong. It was not 22. It was 24. And you can actually see what the countries are. And basically, you get really high-powered passwords like Singapore. And then there's a whole bunch of countries like North Korea, where the only way to go there without a passport is having a North Korean passport, so without a visa. So you could have, of course, change this and actually say, well, I don't really want to go to North Korea. So you could have done a conditional there to actually write it down in different ways. Okay, and one thing I did here is like I went over quickly is like I could run this like as multiple constraints, or with the linear algebra notation of A times vector, matrix times vector, greater than or equal than something. A trick that I did, which is a Julia trick, which is this dot. That dot actually makes it so you actually broadcast. So if you're writing down something that I want to say something equals something else, but I want it, then they're containers, let's say they're vectors, and I want to do an equal component-wise. If you had a dot, usually Julia figures out what you actually want to do. And in this particular case, it knew I had I'm multiplying a matrix times a variable, and I'm getting a vector of variables. I'm getting here a vector of affine expressions of the variables. On the other side, I have only one number. But I can figure out as like, oh, you mean that I want that each one of these affine expressions should be greater or equal than 1. If I added a vector here, a general vector, it would do it component-wise greater than equal. And this is not only clever, it's going to be written in a performant way to make it work. If you nest a lot of these dots, things work out well. It doesn't do extra loops that it didn't need to do. So let me go now a little bit on the details of the, yep. They probably are multiple. I haven't really checked, but I bet that there's probably multiple optimal solutions. Because I would say the covering these high-powered, so Singapore, so I think probably you replace Singapore with, again, I think Sweden was one of the other high-powered ones, then probably also works. So the next step was like so my wife's an immigration lawyer, so of course we had like a long discussion of like, well, can you get all these passports? So probably not, because some of them are incompatible. So then the next question, and making it more interesting, is like, what passports can you get? Out of the feasible passports, which is not an untrivial thing to actually find out if you even can get them, what's the best you can do? And the next one would be, well, it takes time to get the passport. What's the fastest way to get the passport? And what is the method? So it's like, okay, so you need to go and live in this country for a certain amount of time, invest a certain amount of money in this country, marry somebody from that country. You can divorce them in 3 years and then marry somebody else, and you can really go on. And the funny thing is, like, I'm pretty sure that this company, that's what they do. So,
Does this guarantee? Is there a guarantee that this result is optimal?
oh, so this one is optimal in a number of passports. Oh, because I'm using GLPK, which is guaranteed to give you the global optimal solution. A global optimal solution. It's not the only one, but it'll give you, you cannot do it with 23 passports.
Can you get other ones?
I could, yes, but GLPK doesn't have a pool?
I know GLPK, but if it's not
Right, so I can't get it with GLPK, but I can get it with other solvers. But what I could do is, I could actually get the solution that I get, and I can add a constraint that will exclude only that solution. And then I could repeat, and now you're tempting me, because that would be like doing that, but that would be an integer priming class, not really a JuMP tutorial. But you could do it by hand, but some solvers do it automatically as well. And again, I guess the other detail is like, this is optimal up to the numerical precision of floating points, but in exact rational version. So I can actually get the true optimal 24, not up to numerical precision, but perfectly mathematically proven that you cannot do 22. And that's just like changing a parameter on the solver itself. And basically that GLPK runs with JuMP and makes rational calculations when it needs to. So yeah, and again, one of the good things about the whole point of JuMP is that those kind of things, you want to like, oh, I have to figure out how to exclude the solution that I have. That's a math question that you could do. And then I'd really like to go and change the constraint and add it very quickly. And maybe I'm going to do a loop that's going to go and solve the problem, get the solution, add the constraint, and repeat and collect all the solutions quickly and save them and show me all the possible solutions. And the key is I want that to be fast. I don't want to, so I could have written a code that's very similar like this in a language like AMPL or GAMS, but then you start doing for loops and things actually start becoming slow. So the key is that we want it to be as easy to use as AMPL or GAMS, but we want the performance of a full-fledged and performant language like Julia. Okay, so let me see what time we have. Okay, so let me go a little bit more into the details. I went quickly over the notation. So what I'm going to load is, again, I'm going to load JuMP. I'm going to load math opt interface, which is sort of the underlying library that connects JuMP with the solvers. And Benoit is going to talk about that. Is Benoit? Benoit's going to talk about that. Yeah, on, when is it? Tomorrow afternoon? Yes, tomorrow afternoon there's going to be like more details on the internals of JuMP and math opt interface, and a lot of new things that have been developed. So I'm going to go over quickly about like the syntax. There's been some syntax changes from 0.18 to 0.19, which is the current version. I think there might be, what was that the change on his mouse? So there's a change, a pending change for, okay. So here to define the optimizer for the model, you need to write down with optimizer and GLPK. This will change slightly in the next version, but it shouldn't be a big major change. It'll change before we get to 1.0, which I guess Miles will talk in the afternoon about what's the roadmap to get to 1.0. So again, this is the definition of the model and the solver. Here, I'm actually giving a parameter to the solver saying I want the output, the message level to be at level 4. Before I had it at 0, so it wouldn't print anything. Here's where I could actually add parameters, for instance, tell the solver, solve it with exact rational arithmetic so I can have guaranteed solutions. And if you have more complicated parameters for other solvers, that's a place where you can also pass them through. As I kind of illustrated, the variable notation is you can write down variable, you tell it what model, you write down the variable, you can give it bounds immediately. So that would be a simple way of defining one variable. Constraints also have sort of a natural notation, that a way that I would write them in paper if I'm doing simple things. To define the objective, the only difference I need to define is I'm maximizing or minimizing. And then to solve the model, I just say optimize the model. And I generally, adding that JuMP.optimize, make sure that there's no incompatibilities, maybe some other packages using optimize and you don't want to be confused. But if you only were loading JuMP, you might have forgotten about the JuMP. You don't really need to add it. But it's good practice to keep it. So if you load another problem, there's no ambiguity. And in this case, GLPK gives me a little bit more information about the output and it solves the linear optimization problem. I can get a lot of information about the model, so I can ask it, does it have a solution value? What was it, the termination status? In this case, you got an optimal solution. Does it have a primal solution? Does it have a dual solution? And basically, there's a lot of extra parameters that you actually get now from JuMP. There's a lot of information. So Benoit, are you talking about like solver statuses on MOI and stuff like that? So if you want to know more about the details on about that, you can go to the tutorial. These are all things that an optimizer will want to see, and in some sense, we're trying to expose all the details that are behind the scenes from the solver. So now you can really use it to do state-of-the-art research and optimization as well, and it's giving you all the information. Yes.
But does it depend on the solver for the information?
So the idea was to get it so that it's sort of like solver independent, but the information that solvers will give you might be different. So it'll also even more, it'll depend on if you're solving an LP or an IP. Dual status will say, I don't have a dual solution. But that's not because there's any problem. It's like IPs don't give you a dual solution. So in some sense, the interpretation will be some solvers might not be able to tell you that they have that something happened. But this the idea was like to be generic enough that this would be things that would cover everything that you would want to query from the solver. You can still query the solver directly to get other things. So anything that's not defined in MOI should cover almost everything that you want to do, but anything that's not covered, you can still access it and get any specific parameter from the solver. So again, that's like, we really want the technical things, but I will talk more about that because I guess it's like, it is rather technical, but it is useful if you really want to actually exploit the solvers to its full capabilities. So perhaps this one's like an interesting one. So I would like to know if I have a feasible point. I could have like, I have no solution. I do have a feasible point, nearly feasible, infeasible point. I have infeasibility certificate. So now as you go into detail, it's like, you need to know, well, what's an infeasibility certificate? And it starts getting like, I really now need to know optimization. One of the things, the other great thing about JuMP is like, it's an easy way to start playing with optimization without knowing too much and just start modeling things and solving. But then quickly you can go and learn more about optimization when you realize like, I really need to learn more to understand all these things. And which means that even if you go all the way to being an expert, you can still keep using JuMP. So in some sense, the great thing is that it's the same place where a beginner optimization optimizer can start playing with. And it's the same thing that state-of-the-art researchers will be using. So it grows with you as you go. But for now, you can ignore this unless you want to. And if you want to know more, definitely come to the advanced tutorial. I guess more, what you definitely do want to know is how to get the values of the variables of the optimal solution, so you can do it with value. The objective value you get with objective value, and you're actually asking the objective value of the model. So in this case, it was very, very simple problem. You can also name constraints. So in this case, I'm naming this inequality as inequality. And that can be useful, for instance, to delete constraints or to get dual variables, dual values for the constraint later on. So in particular here, what I'm doing is I'm going to delete the inequality from the model, and I can actually resolve it, and I'll get a different solution because I deleted that constraint. And again, I named it so that I could delete it. And this inequality is a Julia variable that contains a pointer to the inequality. And you could have, if I had multiple constraints, this could be a container that has a lot of constraints numbered in whatever way that I numbered when I actually defined the constraint. So let me see. So I guess a perfect segue for collection. So I guess the other thing that I can do is what I wrote now, I had one inequality and two variables, and those were, I could have contained constraints or variables. So if I want to write down a vector of variables, it's the very, very basic notation that we saw for loops and comprehensions. So that will give me a variable that actually is an array of variables. And you can see that it is an array with one dimension of variable refs, which are these objects that point to the variables of JuMP. I could do more complicated constructors. So I could do a matrix that's indexed on the first index from 1 to 10. And on the second one is indexed by red and blue. And I can do that. And basically, I'll get the corresponding object that is defining all the variables. I can also add conditions. So I can do the first component is 1 to 10, and the second one goes from I plus 1 to 10. So if I want to do something like a upper triangular matrix or a symmetric matrix for that matter, I can also write it in that way. I can write down complicated conditions. So maybe I say, well, I'm only going to get things that are either have an even number on the first one and red on the second component. So I can again use the same notation I would use for a comprehension to define more complex containers of variables. I can definitely use the sum notation for any of these containers. So I can sum x of I for 1 to 10, or I could actually just say sum of x. It would have given me the same thing. So I can write that. I can alternatively just write sum of x. and it should give me exactly the same constraint. But of course, here I could have added, let's say maybe only up to 6, and it would give me a different thing. You can do more complicated things again with conditions. Here I can again say from 1 to 10, C in red to sum all of them. I can again add this is even condition to write it down in a more complicated way. And generally you get a nicely printed version of what is the constraint that you actually wrote down. Let me see, what else do we have? So the for all notation, I showed a little bit. If you add the for all, basically that for all notation goes in at the beginning, where I'm naming the constraint, and I can name it and define over what I'm actually looping to generate the constraints, or I can define them without explicitly stating what the name of the constraints are. And again, I could recover large bounds, so I can look at the second constraint. Oh. No, that one. Okay. 2. I can recover constraint 2, which was x2 less than or equal than 0.9. So I could go and modify that constraint as well, or like get the dual value of that constraint and so on, or delete it. So I've looked only linear inequalities. So let me show you a little bit more about what other types of inequalities you can get. So I guess David already pointed out the idea of using the matrix notation. So here's a case where I have the matrix A, left-hand side vectors L and U, and I can a vector of variables X, and I can write down L less than or equal than AX less than or equal than 1, that U when I want to do it coordinate-wise, and for that the only thing I need to do is add that dot before the less than or equal. So that's a useful notation to write down things that have linear algebra constructs.
Was that more efficient than doing it explicitly?
That is a
Can you
very...
repeat that? No, repeat what?
Oh, so the question was like, is this notation more efficient than writing it for all, writing in a different notation? I guess once it's compiled, it should be exactly the same, shouldn't it? To generate. So.
And they go through different pathways.
I guess one detail is like, it's probably this one's too easy, but if we have a lot of complex containers that have I, J, Ks, and extremely large problems, code generation of JuMP, the expansion of the macro could be an issue. But I guess it's like, Benoit, you're talking a little bit about containers? And okay, so then it's like, if you want to know more, there's some issues with performance that actually have been significantly improved for JuMP, and you can actually generate your own containers to be able to improve speed. If you have very complicated graphical structures, for instance, it might make sense to pay attention to that. And that is a lot of the things that went into MOI. So in this case, yeah, I think here it shouldn't be a big difference. Yeah, no, there's no special linear algebra. There's no special use of linear algebra in JuMP yet. Is this linear algebra here? Is this operation using whatever Julia can do, or is it a?
You specialize.
It's specialized, okay. But it's not if somebody goes and redefines. So if this thing was an operator, and you could do an operator on the vector, an abstract operator, would JuMP be able to use that? Let's say that I define this as a type, and I say that's a dot x, and that's the identity.
It should work.
So actually, I guess we can try it. No, I guess.
You use the
Okay, perfect.
Don't rewrite these expressions, so it doesn't necessarily
Translate but any guesses on what will happen with that I there? So I guess maybe before I start, like maybe I should say like I times that operation is like the EYE from MATLAB, but it's not the EYE from MATLAB is the identity, and it realized like if you're multiplying the identity by ones, I don't really need to pick that matrix and multiply by the ones. I can just give you back the whatever vector you gave me. So that will be much more efficient. Now, no idea what will happen here, so I guess we'll see. It worked. Is the operation here being is it creating the matrix and translating and multiplying it internally, or is it actually using the operator?
I think it's not creating the matrix.
It's not creating the matrix.
It works with abstract matrix.
It works with abstract matrices. Okay.
It's probably not optimized for doing like fast addition to the outline expressions for each individual. So it probably goes to the fallback method added by the identity operator, not by JuMP.
The default method by the identity operator. So then it looks identity. It picks us a vector of variables. It operates the identity and it gives you back the vector of variables.
So it probably does the smart thing for identity operator, but not on the JuMP side.
But not on JuMP. So yeah. So but that's like so what I guess the detail was to say like this is something that JuMP was not aware of. Oh, I could use the identity operator, but that Julia has built in, or some other package that's built in, and suddenly JuMP took advantage of it automatically. And that's something that is nice about Julia is like packages usually combine somewhat seamlessly, and even more, you can get extra performance for free from another package in your own package. And usually, unless you do, usually that happens sort of automatically. Although I guess here it was like it wasn't completely clear what exactly Julia was doing. But again, there was a vector of variables multiplied by the identity. We got a vector of variables, and then JuMP took over and did something else to construct the affine expressions. I guess. Okay, I could go on for. I was thinking about adding extra stuff. Now I'm actually trying to think, how can I break JuMP by adding extra things? So, other comment: if you would like to break JuMP, please do so. It's like it's a good thing if you break JuMP, you fix it. But there's always going to be somebody who's going to help you fix it. So, let me see. And okay, so basically, just like very quickly. You also can actually write down quadratic constraints. They could be convex or non-convex. If you're going to get a global optimal solution or not will depend on the solver you're using, but JuMP allows you to write it down. Very importantly, you can also write down conic constraints. So you can write down semi-definite constraints. You can write down second-order constraints that look like norm of some affine function less than or equal than some other affine function of variables. It's also rotated second order cone if you know about them. And so basically a lot of the new interface allows you to write down generic conic optimization with traditional cones or even newly defined cones that you might actually want to look at. And one of the talks on, I guess, Wednesday or Thursday? No. Wednesday, we'll actually look at sort of optimization with general cones. And there's, I guess, more than one of the talks will be about that. And basically JuMP is prepared to actually be able to work with the generic cones. And finally, you can also write down general nonlinear expressions. I guess this one's a little bit boring. It's still quadratic, but you can write down exponential sign. And if you had the right solver like IPOP, you should be able to solve it. And again, we're back on the pre-compiling IPOP, but you can actually give it, and there's a lot of extra features that'll skip about like you could potentially write down here instead of x, you can write a function that is a Julia function that does something. You can register so that JuMP knows how to use it, and JuMP will be able to, IPOP basically needs the evaluation and the gradient of these functions. And basically, there's some built-in automatic differentiation into JuMP that will allow it to do automatically. You just need to define the code for that function that you're defining there and do a couple of small things to actually make it work.
So that x and y seem to be any real number?
In this case, yeah, x and y are any real number for the x, but this could have been an f that I defined somewhere else. I need to do a couple more steps to make it work, but it could have been any Julia function, almost any Julia function. This one in particular, this IPO just finds the local. So it will only be global if the problem was convex. But that's because IPOP can only solve the local optimality. Is there any global solver working right now in JuMP 019?
ON Not easy to install, but it works.
It works?
Does Darren work? Yeah. Darren works.
In 019?
No, I don't know. So you just don't have any, I don't know a solution.
No, for IPOP, you don't. But if you called it with a global solver, you would get and apparently I guess Gwen might be the only one that will run soon. I don't know when Baron will gonna run. So if you have a global solver that you could plug into JuMP 019, wink, wink, it'd be really great if you actually can build the interface. And if you want to know how to build the interface for the solver, you should definitely go to Benoit's tutorial. And I guess there's going to be collaboration time. So maybe go to the tutorial on Wednesday and build the interface, and maybe we'll have a global solver running in Thursday. Skip is only. See, so now you have now it's a race to see which ones to say the first global solver to.
But it can't do sign. Skip can't do sign.
Skip cannot do sign. That's actually true.
So I actually want somebody else to build the interface. That's what I mean, really.
So yeah, but I was like, the easiest way to get somebody to do it is like you start doing it and start asking for help. Eventually, somebody else is like, oh, come on, okay, I'll do it. Okay, and I think we're just in time, so hopefully that gave you an overview, a little JuMP. There's a lot of notebooks out there, so you can download these. There's a lot of extra things to do. The manual is getting, I would say it's fairly reasonable at this stage. It's gonna get better soon. So Miles, I guess we'll talk a little bit about what are the steps to get to JuMP 1.0. One of those is getting more documentation and more examples. But again, while you're at the workshop, definitely feel free to ask anybody if you have questions about how to implement a solver or how to use a given solver or a given feature. We'll be here all week. So thank you very much.
So we have three.
The mic was off.
No. Well, it seems that the mic was off, but that's okay. So now we have a free lunch time until 1 p.m., which will start with the main talks on the main welcome. So people from who are not from here, just get a hold of some locals, and we can just start going around downtown. So we can find places to okay. So yes, thank you.
And we're back at 1 o'clock
Yes.
for the plenary sessions and the official opening of the. Okay, so esto fue complete beta test de que la tecnología. ¿Y el micrófono acá ha funcionado?
Ah, bueno.
Bacán,
Sí, mira, mira.
apagado. Ah, sí, hola, ok.